Hi class, we meet again. In this video, I'm going to show you what does it mean by open system. We are going to describe the nature of open system, and then we will see how to express the energy balance equation for your open system. Next, we are going to observe the workflow inside the open system, and then apply the first law of thermodynamics in your open system. Alright, so up to today, we have seen what does thermo covered. The first thing you need to know about the system, and then what type of working fluid that you are using, and also the law. So for the past 4 weeks, we have seen that closed system you have two. One is a rigid body, and another one is your moving boundary work. And as for moving boundary works, it is subjected to 5 processes, which is isothermal, isobaric, isochoric, polytropic, and also adiabatic. So in this video, we are going to continue about open system and how are we going to apply your first law inside your open system. But before that, you need to understand what does open system means. So the first thing, let's have a look at this 3 picture that we have here. So open system means that you are going to have one opening and there's another opening at the end. So if we are going to label this is going to be your inlet, or usually we don't note it as 1, and it's going to have the outlet, or we noted it as 2. So we have learned before that in thermodynamics, your energy can be transferred in a form of heat, in a form of work, and also in a form of mass. But for a closed system, the energy can only be transferred in a form of heat and work because your mass is constant. But now in your open system, where you have inlet and the outlet and your working fluid, in this case, your working fluid could be water, which is vapor type, or you can have let's say you can have an air, which is ideal gas category. So that's the type of working fluid that flows inside your system here. So let us recall back, you have a system and this is the boundary, but in this case we name it as open system because you have an inlet, and then let's say inside here is water, so it's going to flows until it goes out here, right? So a popular example that I can give you is the water dispenser at your home, like Kowe or Kuku. So you have a water flowing in from the sink, and then it's going to flow inside this chamber. And since you want to have a hot water, so they are going to have electric heater here. That's why by the time the cold water goes inside this circular tube, so as it receive the heat from your heater, so at the end of at the outlet of your where you press your water for to have a drink, so it's going to be a hot water. So where does it receive your heat? It comes from your electric water heater. So let's say maybe you put your electric water heater somewhere around here, right? So this will give your Q in, or heat addition. Okay, and this concept goes the same with your water inside your bathtub here, right? Where you have one tap flows in, but you don't close the other end here. So whatever water that flows in here are going to be the same amount with the water that's going out in this part, right? So this is what we call as mass conservation, where mass in must be equal to mass out, and you bring your mass out over here, so you are going to have the change of your mass. Alright, so now let's have a look at your notes, right? You have the first law of thermodynamics of open system. So consider a fluid flowing in a steady flow with mass flow rate m through an apparatus. So you have an apparatus over here where you have an inlet and you have an outlet, and then it has the electric heater here which produces heat, right? And it's also have this fan over here which going to have work output in here, right? So recall back that in thermodynamics, your energy can be transferred in a form of heat, in a form of work, and now that we are in open system, so you have another one which is in a form of mass. So as the working fluid, let's imagine that you have a water flowing inside the system. So you are going to have mass inlet is equal to your mass outlet. So what does mass flow rate means, right? How are you going to calculate for your mass in and your mass out? So mass flow rate is, by definition, is m dot is equal to your density times with velocity and also the area, the cross-sectional flow area, right? So what does it mean by cross-sectional flow area? Imagine you have flow in here, right? So this flow is going to touch this surface that you have here, right? And it is actually perpendicular, right? So that is why we are going to times it with your area, the area where the flowing water touch the area. So if you are going to have a circular pipe, so the area is circular. If you are going to have rectangular or let's say square or rectangular, so you are going to have a area of rectangular or area of a square. And in this equation, why is that you are going to times it with your velocity? Because m dot, we need this m dot is a flow rate, so you are going to have m dot, sorry, so you are going to have the term of m dot, which is kilogram per second. Right? So as I have told you in your class, you need to have a homogeneous unit. So in this case, your m dot is kilogram per second. So in order to get that, you are going to have your density, which is in kilogram per meter cube. And since it flows in this direction, where you have this area in circular, so you are going to have the area here, which will give you meter squared, right? And the velocity, because the water is flowing, so it's going to have a velocity flow, which is in meter per second, right? So if we arrange the density times with your A times with your C, so you will have kg per meter cube times with your meter squared times with your velocity, which is meter per second, right? So in the end, you are going to have kilogram per second, which is the unit for your mass flow rate. So this will be useful when you wanted to calculate for your m in and your m out, or sometimes denote as 1 and this one is denoted as 2. Alright, before we go further with your steady flow energy equations, alright, we need to understand first, what does steady flow energy equation devices relate to your open system? Okay, so what are steady flow energy devices? In this in this topic, you are going to cover about nozzle, and then you have diffuser, turbine and compressor, mixing chamber, heat exchanger, and also throttling device. But for your class, we are going to cover only these 5, which is nozzle, diffuser, throttling valve, compressor, and your turbine. Alright, so let's recall back last time in your energy analysis of your first law of your closed system, you have this energy balance, and then when you expand it with first law and reduce it with first law closed system, so it's going to left with you your heat, your work other, it's either electric or fan work, and your moving boundary work is equal to your internal energy, where your moving boundary work here, right, will be depend on the 5 process that you have, right? For example, if you have a pressure constant, so your moving boundary work will be pressure V final, or we note it as V in V2 minus with your V1. Okay, but now in your open system, it will be depends on the devices that you use, and in our class we are going to cover these 5 devices, right? The other two, you will meet these 2 things in your when you further into your air conditioning classes next semester. Alright, so in next video I will show you how does your energy analysis, how are you going to apply your first law inside your energy analysis for your open system. So it will eventually looks like this. You start from energy balance equation, and then you expand it into heat, work, and then you will see where does this moving boundary work goes, how does it comes into this enthalpy term, and how can we apply this kinetic energy and potential energy inside your analysis based on these 5 devices. All right, thank you.